correlation measurement actually is. There are many. But the one that is in the most use, shall we say, is what's called a Pearson's product moment correlation coefficient, or simply Pearson's correlation coefficient, or sometimes just the correlation coefficient. If people are saying correlation coefficient and not explaining anything else, with no names or no prefixes to it, this is what they're talking about, what we're going to say. It is one of the most commonly used measures of correlation, though strictly speaking, not the only one. It's a statistical measure that quantifies strength and direction of a linear relationship between two continuous variables. Now, this is a little controversial, because in this entire idea of correlation, I only talked about positive, negative, strong, and weak. I never talked about straight lines. But it is a fact, so to speak, a mathematical fact, that the value of this particular correlation coefficient is high or low. It is close to +1 or -1 or close to 0, depending on whether there is a good linear relationship between them or not. It took some time for statisticians to understand this, but this is now well understood. So, the correlation, idea of correlation, picks up a linear relationship. It's not obvious in the formula, but that's what it does, and it's good to keep this at the back of your mind as we flow through into our analysis of linear regression. We're not going to talk about too many formulas in these sessions, but here is a formula. What this formula tells you is that if you've got n points, x1, y1, x2, y2, x3, y3, imagine the case that n is equal to 10. So I've got 10 pairs of points, 10 advertising expenditures and the corresponding sales. I've got 10 pairs of points. An Excel sheet, I've got 2 columns. So I've got 10 pairs of points. One I'm calling x and one I'm calling y. Which is x? The variable that I'm using to predict. Which is y? The variable I am predicting. But in the correlation coefficient formula, you see that it's symmetric to x and y. So the correlation of x and y is equal to the correlation of y and x. An important point. But for now, let's stick to the formula. So what does the formula say? So the formula says that if I've got n pairs of points, then I'm going to calculate this thing in the numerator, which essentially says that xi minus x bar multiplied by yi minus y bar. Now you may have seen what this bar notation means. This bar notation means average, arithmetic mean, average advertising, average sales. So now, let's think about this. Xi minus x bar therefore means how much is, say, advertising above average advertising. And yi minus y bar means how much is sales above average sales. So now think about this. Think about this product. Xi minus x bar, yi minus y bar. Stare at that and ask yourself a question, since we're talking about positive and negative correlations. When is this product positive and when is this negative? It's going to be positive when xi minus x bar is greater than 0 and yi minus y bar is greater than 0. Or I have above average advertising and above average sales. It will be negative if one of them is negative. In other words, above average advertising and below average sales. That's less likely, is it not? It will also be positive if both are negative. High advertising, high sales, low advertising, low sales. So therefore, you can see that the pattern of the data dictates whether this will be a positive number or a negative number. The thing in the denominator is always positive, so it doesn't impact the sign of R. This denominator, for those of you who have seen such things, should remind you of variances, variance of x and variance of y. But for now, we don't need to bother about that. Just remember that is positive. The sign of the correlation is determined by the numerator. And this will be positive this total, the sum of these pairs, product of these pairs will be positive if most of them are either both above average or below average. It will be negative if most of them are such that one is above average, one is below average. And that will happen when? Think of my price example. An above average price will lead to below average sales, a negative in that product. Similarly, a below average price, negative in that product. So advertising and sales will make this number positive. Price and sales will make this number negative. The purpose of the denominator is to tie down this number to -1 and +1. Because I can always change my units of x and y to make this numerator whatever I choose to. I choose to measure sales in thousands of units. But now I choose to measure sales in single units. So if I sell 1,000 phones, I can measure it as 1 unit in thousands or 1,000 units in units. So I can change my numerator to whatever value I sort of choose to by changing units. Not good. I can't interpret numbers that way. So I now know that when I change units, something in the denominator would catch on to that and say, okay, the denominator will also adjust so that the number stays between -1 and 1. That's all I'm going to talk about here, but you're welcome to hack this formula. It's an interesting formula to get your hands around and just execute on even a spreadsheet. And most spreadsheets allow you to calculate correlations. Even calculators allow you to calculate correlations if you give them pairs of numbers. Now, once this formula has been calculated, and once again, you will not do this manually. There will be some calculator, some spreadsheet, something that will tell you how to do that. There's an important point to be made here. In the formula, as pointed out, there was no distinction between x and y. The correlation between x and y is the same thing as the correlation between y and x. What does that mean? It means that correlation is not picking up the fact which is an input and which is an output. It is not telling you that if advertising increases, sales increases. It may just as well be telling you that if sales decreases, advertising decreases. Correlation is not causation. Correlation is not causation. Using a correlation between two variables, you will not be able to say, just from that one number, which variable is changing first and is influencing the second variable. Correlation is symmetric in its input. So therefore, as advertising expenditure increases, sales increases. And this is a positive correlation. But does it mean that advertising causes an increase in sales? Maybe, but not because they are positively correlated. We have to dig deeper for that, not because of this. Causation is a very tricky aspect, and many domains such as economists and computer scientists have tried to understand causation. And in some situations, for example, in understanding key factors, causation is really important because I'm changing advertising and I'm expecting it to influence sales. In certain other applications like forecasting, causation is not that important. So long as I know that I have a predictor variable, I don't need to know the causal relationship between them. So long as I know that there is a predictive relationship between the variables, I don't need to know how it is causing things. And so therefore, please do not confuse this. To solve this problem of causation, we'll need to look at other variables, other factors, relate that to other things, maybe have intermediate variables, maybe have latent variables, maybe have unobserved variables that will help us do this. More complicated, we will not address that question very clearly at this time. But in your journey in machine learning and artificial intelligence, this may turn out to be something that will add business value. The understanding of causation is central to many business problems. And as business leaders, you may be called upon not to think about correlation, but to think about its implications for causation. But enough of that for now. To convert this almost philosophical problem of causation into something that makes statistical sense, what you can do is you can look at certain other variables and see whether I can tease apart a relationship that may point to something more logically causal. For example, we can look at, say, this data on sales and advertising, and let's split it into another factor, let's say an economic zone. And in economic zone 1, let's say this is what the relationship is. Remember, every point represents what? Represents a region. So I'm going to take these regions and I'm going to divide them into multiple zones, say 2 zones, zone 1 and zone 2. So look at all the points that are in zone 1 and plot them. And let's say this is what you get. And now let's take a look at zone 2, which is the remaining points, and this is what you get. Now there could be many reasons for this. Zone 1 could be something in which the economy is doing very well. Zone 2 could be something in which the economy is stagnant, so to speak. But there could be many reasons. But what we do know, irrespective of the economics behind this, we do know from a statistical perspective that the correlation is essentially being driven by whatever is happening in zone 1 and not by what is happening in zone 2. So if on the left plot, if I see a positive correlation, I should try to understand that or get its causal effects more on data from zone 1 than from zone 2. Because zone 1 correlation is actually much greater or closer to +1, shall we say, than zone 2, which is closer to 0. This is one trick that's often used so that we can get a data-driven look at causation and allow the data to try and determine where might correlation be coming from. And this points to saying your correlation is coming from some effect that is present in zone 1 but is not present in zone 2. And now you have more information and you can dig a little deeper. As we said, this goes a little beyond our mandate for being able to build equations, but it is still something that as leaders, you should be mindful of as we build relationships. When does it hold? When does it not hold? When does it hold more strongly? When is a relationship actually weak? And some data mining exercises there could really give very interesting insights. So, to end with, correlation is not causation. Variable 1 being variable 2 being correlated does not mean that change in variable 1 will automatically lead to a change in variable 2. There could be other factors at play here.